Okay, the recording has started. So let's start. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL-PMRF Teaching Assistant for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. He is a faculty in IIT Kharagpur. This is a 12-week course and we are in the fourth week of problem solving session. So up to 3 weeks, we have discussed about the algebra of sets, the random variable, different definitions of probability, types of random variables is there also, and then we have discussed about some special kinds of discrete distribution, and today in week 4 we will discuss about spatial continuous distribution. And before that we will discuss one more important probability distribution, which is discrete in nature, that is Poisson distribution. So in week 4, we will discuss about Poisson process or Poisson distribution. This is discrete in nature. And besides these, we will mainly focus on continuous distribution. Okay, like exponential, gamma, beta, etc. And then we will solve some numericals based on these topics. So let's start with Poisson distribution. The probability mass function for the Poisson distribution is like, suppose x follows Poisson distribution. It has one parameter, lambda. So the probability mass function is written as like e to the power minus lambda, lambda to the power x upon x factorial. Here the support for the random variable x is 0, 1, 2, and so on. Okay. So this is the probability mass function for the Poisson distribution. Poisson distribution is a positive, like Poisson variate is a positive random variable. Okay. There is no negative random variable in case it is a Poisson variate. Now, the expected value of the Poisson variate is actually the value lambda itself. Okay. Again, the variance of the x also equals lambda. So this is the only distribution where mean and variance have same magnitude, okay, which is equals lambda, the same value as parameter. Also, if you may wanna know, the third order central moment for the Poisson variate is again nothing but lambda itself. Okay, so first three central moment is lambda for Poisson variate. Also, like the skewness. So the skewness is like the beta 1 coefficients, which is mu3 square upon mu2 cube, which is nothing but lambda square upon lambda cube, comes out to be 1 by lambda. Since here lambda is positive, greater than 0, so this implies it is always greater than 0, which is positively skewed distribution. Okay, so Poisson distribution is a positively skewed distribution. Okay, also, it's MGF. Uh, Again, let me first write the kurtosis. The kurtosis is like beta 2, which is mu4 upon mu2 square. This comes out minus 3. This comes out to be again 1 by lambda, which is greater than 0. This implies Poisson variate is leptochotic in nature. So this means it is more peaked as compared to the normal distribution. Okay. Now the moment generating function is expected value of e to the power tx, which comes out to be e to the power lambda, and it's e to the power t minus 1. Okay. So this is the description of Poisson distribution. Okay. Also, there are some notes actually, like the relation between binomial and Poisson actually. Okay, so as you people have known that x follows binomial and p, then in that case, the probability mass function for the binomial distribution is NCX, p to the power x, 1 minus p to the power n minus x equals 0, 1 up to n. Okay, so if n tends to infinity, that means for a sufficiently large value of n, and p tends to 0, that means very small value of 0, this quantity np is nothing but a finite value, say lambda here. Okay, so in this scenario, when x is a binomial random variable, and for large n and for small p, this binomial random variate converges to a Poisson. So binomial converges to Poisson when n is large and p is small. Okay, and the average value is nothing but, in case of binomial it is np, and in case of Poisson it is lambda itself. Okay, again the next distribution is like now spatial continuous kind of distribution. So the first one is uniform. So the uniform distribution, since it is a continuous uniform distribution, so suppose x is a random variable which follow uniform distribution with, let me write a and b. You may write any value. Let me write a and b. So the probability density function fx equals 1 upon b minus a. X belongs to a to b. A and b is any real number. A is greater than b. So this is the uniform, the probability mass function for the uniform distribution. Okay. Now you can also calculate its CDF. Its CDF is actually capital Fx. Will be like this. It's x minus a upon b minus a. Okay. The same support. The average value, the expected value of x in case of continuous uniform distribution is b plus a by 2. And the variance of the uniform variable is b minus a whole square by 12. Okay, you may solve this. Okay, I'm just writing the direct formula expression. Now the moment generating function for this is e to the power bt minus e to the power, it's 80. It's divided by p times of b minus a. This is the moment generating for the uniform distribution. Similarly, we have more distributions, like one of the most common one is exponential. The exponential distribution. The exponential distribution, the suppose x is a random variable which follow exponential distribution with parameter, you may say lambda, theta. whichever you like to write. The PDF for this distribution is, we have two form actually. Okay, you may either use lambda e to the power minus lambda x. Here, lambda is greater than 0, x is greater than 0. Okay. In this case, the expected value of the exponential random variable is 1 by lambda. Okay. And the variance of the variable is 1 by lambda square. Here, if you will calculate the skewness and kurtosis, you will find the beta 1 comes out to be greater than 0 and the corresponding beta 2 also comes out to be greater than 0. This implies it is positively skewed and leptocotic in nature. Okay, so this is the exponential distribution. We may change the extent of skewness and kurtosis by varying the parameter value. Okay, but it is always like positive in nature. Wherever I can recall, the exponential distribution is either highly positively skewed or slightly positively skewed, depends on the value of lambda only, but always skewed. Okay, and similarly for kurtosis. Now the now it's MGF. Its MGF will be like expectation of e to the power tx, which comes out to be like 1 minus lambda t whole inverse. Okay, so this is its MGF. We have a lot of questions based on these topics actually. We will solve. The next is like gamma distribution. Okay, let me write one more thing actually. I alternate form actually. Here, actually, there is nothing difference in these form actually. Here the fx is lambda e to the power minus lambda x. So here it is 1 by lambda e to the power minus x by lambda only. There is nothing difference. Just the expected value of x is like lambda here, and variance of x is lambda square. Okay. Now the next distribution is gamma distribution. So suppose a random variable x follows gamma distribution with parameter alpha and beta. Okay. So its probability density function is like beta power alpha upon gamma alpha. It's e to the power minus beta x to the power alpha minus 1. Here x is greater than 0, alpha and beta is greater than 0. This is the probability mass function for the gamma distribution. If if you will solve the cumulative distribution function CDF for the gamma distribution, you may find an incomplete gamma integral. So its CDF directly cannot be like written in a closed form. Okay. Also, but some numerical techniques, you are able to calculate the expected value of x, which is like alpha by beta here, and the variance of x is alpha by beta square. Okay. Now there is one more thing actually. If you are recalling the CDF PDF of the exponential distribution, this one fx lambda e to the power minus x, lambda x. If you put the value of alpha equal to 1, suppose let we put alpha equal to 1. Then in that case, the fx will be like it's beta, it's gamma alpha, that means gamma 1 equals 1. So it's beta e to the power minus beta x to the power 0, that means 1. So beta e to the power minus beta x. And this happens x is greater than 0, alpha equal to 1, and beta is greater than 0. Obviously, this is nothing but a special case for exponential beta. So this implies gamma converges to exponential distribution when alpha comes out to be 1. And that is actually a shape parameter. Oh, okay. Maybe I put it wrong, maybe shape or scale. I think it's a shape parameter actually. So on the power. So yes, it's a shape parameter. When the shape parameter equals 1. When the shape parameter equals 1 in gamma distribution, then the gamma distribution converted into a exponential distribution. So this implies like every distribution are connected to some other distribution via some assumption or some particular value or maybe some other transformation method, like the Poisson converted into binomial, even the binomial converted into normal for p equal to 50% or half, and for sufficiently large value of n, that we will discuss in next week actually. Okay, so here gamma to exponential, gamma to chi square, exponential to chi square, everything is connected. Every distribution is like connected to each other. Okay, now the next one is beta. The next one is beta distribution. So again, x follows beta. You may write alpha, beta, or mn, whichever you prefer to like. Okay, so it's suppose I have written mn. So the probability density function for the beta distribution is like 1 upon beta mn, then x to the power m minus 1. The 1 minus x to the power n minus 1. Here x belongs to 0 to 1. There are two kind of beta distribution is there actually. Okay, so its support is 0 to 1. Here mn is greater than 0. So this is the beta, the PDF of the beta distribution. Here like beta mn equal to, it's like gamma m gamma n upon gamma m plus n. This is the beta function actually. Okay, and also gamma n plus 1 equal to gamma factorial. Okay, so there is one more thing. If you want, like if you are going to derive the CDF for the beta distribution, again you may not able to compute the closed form for the beta distribution. Okay, so this is the case. Here its mean and variance is also there. The mean, the average value for the beta variate is like m upon m plus n. And the variance, this variance is large. Variance of x is like it's mn divided upon m plus n whole square, m plus n plus 1. So this is the mean and variance of the beta variate. Okay. And there is one last distribution, that is shifted exponential. Shifted exponential distribution. Here we shift the random variable with the help of the the location parameter, not scale parameter, the location parameter. Okay. So the PDF form is like, suppose 1 by sigma to the power minus x minus mu sigma. So this is the shifted exponential distribution where x is actually greater than or equal to mu. Sigma is greater than 0 and mu belongs to the real number r. Okay, mu may take any value, but x minus mu must always be positive. So the average value for the shifted exponential is like mu plus sigma, and its variance will be like sigma square. Okay, so these are some of the distribution which are commonly used in continuous random variable format. Okay, and these are actually used by us as well in our research work. So there is one more property. Actually, in last lecture, we have discussed about memoryless property. You may recall. This is also known called as like termed as lack of memory property. So the probability that x is greater than m plus n, given x is greater than m, is nothing but the probability that x is greater than n. So the additional time and the waiting time have the same probability distribution. We have some question on this topic as well. We will solve this. Okay. And yes, the exponential distribution follows the memoryless property. Okay. And in discrete case, can anyone tell me which distribution follow the memoryless property? If you may recall, anyone? Okay. So there is one or two. Am I audible now? At least let me know. Am I audible and my screen visible or not? Now there is some more terms like reliability. So reliability is like just a probability actually. Okay. So the formula for this reliability, you may write either capital RT or small rt or capital Rx or small rx, whichever you would like to write. Suppose I have written T here. You may write X as well. RT. So this is the notation for the reliability function, and this is defined as probability that X is greater than. Okay. And if you may recall, you may also write it 1 minus probability that X is less than or equal. Okay, X. Problem. Let me use the word X here. Okay. So probability that X is greater than or equal to X, which is 1 minus probability that X is less than or equal to X. As you may recall, you may find probability that X is less than or equal to X is nothing but the CDF function. So the reliability and CDF are like complementary to each other. Okay, Rx is equal 1 minus Fx. capital Fx. Okay. So this is what? This means like suppose 2. Let me write Rx at x equal to 2. Okay. So this means what? Suppose equipment or unit has successfully functioning at time point x equal to 2, and then we have calculated or we will calculate the probability that it will function after or it will survive after 2. Okay, so that means it is functioning at time point 2, and then it will survive after that. This is the probability, which is termed as reliability actually. Okay, there is one more term actually, that is hazard rate function. HRF in short. We will usually denote it by small hx. You may use capital Hx as well. So this is the ratio of the probability density function and the reliability term. Okay, this is also termed as instantaneous failure rate. So these are the topics which you may have seen in the fourth week lecture. So from here, we will solve some numericals based on these topics. Okay. If anyone have any doubt, then he or she may ask. Okay. So let's start with question number 1. Okay. Let me write one more thing actually first before writing the question 1. There is one more distribution that is broadly used in reliability and survival analysis, that is Weibull distribution. Okay. The Weibull distribution is also there. Actually, these distributions are like quite complex in writing or nature. So we will usually use this in our research, but in common, those are the above that we have already discussed. Some of the basic distribution that are quite explicit, that has quite explicit functional form. Okay. Now the Weibull distribution, the CDF, the cumulative distribution function for this distribution is 1 minus e to the power minus of x delta to the power beta. Here x is greater than 0. Here like delta and beta are the parameters here, which is also greater than 0. Okay, so its density function, the fx, is like somewhat complicated as compared to the above or previous one. Beta upon delta, x upon delta to the power beta minus 1, e to the power like minus of x by delta to the power beta in the same support. So this is the probability density function for the Weibull distribution. There are some different functional form even exist. Okay, so this is not the only form. The similar kind of forms are there in literature as well. Okay, so obviously since the distribution is not that much explicit or simple form, so it's like expected value and its variance are also not in the very simpler form or very simple form. So its mean values like delta and then gamma function of 1 plus 1 upon beta. You don't need to learn the mean variance for the Weibull distribution. The above one you may learn. Okay. But for Weibull, I'm just writing to let you know that it has complex form. Okay. It's delta gamma of 1 plus 1 by beta. And for the variability, it's delta is square actually. And then it's gamma function here actually. And the first one is 1 plus 2 by beta, then minus, then again it's gamma function, and it's 1 plus 1 by beta square, and then the square bracket closed. So this is the variance of the variable distribution. Okay, so obviously not the simpler form or well-known form to memorize. So these are some of the distribution. Now let's solve some numericals. Anyone have any question up to this point? You may please ask. So the question starts with like the question one is like the number of phone calls over a certain time period. The number of phone calls over a certain time period follows a Poisson distribution. What is the average number of calls? The question is, what is the average number of calls necessary for the probability of one necessary for the probability of one or more. Let me write here one more of one or more calls is at least 0.98. So this is the question actually. So just please read the question once. Here we are given the number of phone calls over a certain time period follows a Poisson distribution. And what is the average number of calls necessary for the probability of one or more calls is at least 0.98 or 98%. Here, let me first tell you one thing. Like every distribution has some like property. Okay. So when a random variable experiment has some nature, like it feels like it gives a rate, okay, an average, a rate kind of thing, then there will be chances that it follows Poisson distribution. Okay. If it is discrete in nature, obviously. Okay. Then in that case, it follows Poisson distribution. It is it has highly chance. So here it is given, we are given a range actually, we are given a rate actually, not range, a rate actually is given there. The number of phone calls for a fixed time period for 1 hour. Every hour we get one call, or every day we got three or four or seven calls. It's a kind of rate actually. So this kind of problem follows Poisson distribution. So let's solve the problem. Here given like suppose let me first define the random variable x. Okay. What is the random variable x? So number of phone calls actually. Okay. So the random variable x is like number of phone calls. Okay. So it's a random variable. Now it follows Poisson distribution with the parameter here, suppose lambda. Now the question says, let me first write the PDF. The PDF for the Poisson distribution is like e to the power minus lambda, lambda to the power x on x factorial, when the value of x can take 0, 1, 2, and so on. So this is the PDF. This is the question. Now we are given one thing, one information. What is the probability that the number of calls necessary for the probability of one or more calls is at least 0.9? So at least this one or more. These are the like keywords we need to focus. So what we need to find? We need to find one or more calls. So x is the number of calls. So we need to find the probability that x one or more calls. So x is either greater than one or equal to one. Okay. So what is the probability that this one or more call has probability at least 0.9? So this probability is at least 0.98. So either it is 0.98 or more than 0.98. So this is the given statement actually. The probability that the number of phone calls is greater than or equal to 1 has the probability at least 0.98. So this is the given question. Now, as we know, probability that x is greater than or equal to 1 can be written as 1 minus probability that x is less than 1 is greater than or equal to 0.98. Okay, simple. Now, since x is a discrete random variable, actually, here you can see x is a discrete random variable and the value permissible for x less than 1 is 0 only. So, 1 minus probability that x equal to 0 greater than or equal to 0.98. Okay, now the rest is to you. 1, okay, let me write the probability. Let me write it directly only. 1 minus probability that x is equal to 0 is what? Here in the PDF, put the value of x equal to 0. So e to the power minus lambda. Let me write here. E to the power minus lambda. Lambda to the power x upon x factorial. 0 factorial comes out to be 1. And any scalar or any number to the power 0 comes out to be 1 as well. Greater than or equal to 0.98. So it's 1 minus e to the power minus lambda is greater than or equal to 0.98. So yes, from here only e to the power minus lambda is less than or equal to 0.02. Okay, not equal to. Okay, so just taking the natural logarithm, so it's minus lambda is less than log of 0.02. Now the lambda is greater than log of minus of log of 0.02. So now this value, if you know, you may know actually, this value comes out to be negative and negative sign is also there. So overall, it comes out to be positive. So the lambda, when you will see the logarithm table, you may find is greater than 3.912. Okay. So yes, lambda is greater than 3.912, and we have actually options there. So the closest one is lambda comes out to be 4. So this is the solution. So we have this question and the given parameter value is 4, which satisfy this condition that is given. The average number of call necessary for the probability of one or more call is at least 0.9. Okay. So anyone have any doubt in this question? He or she may ask. Anyone? Okay then. So let's solve the second question then. Now the next question is like, it is based on actually uniform distribution. So the question is like the total duration of all games, the total duration of all games by one team in one season of a major baseball league, of a major baseball league is seen to range uniformly between 427 hours to 504 hours. Okay. Then the question is, what is the probability that a team will play team will between 479 hours to 498 hours of games in a season? Hope you may find the question. Okay. The total duration of all games by one team in one season of a major baseball league is seen to range uniformly between 427 hours to 504 hours. Then what is the probability that a team will play between 479 to 498 hours of games in a season? Okay, simple. It is a uniform distribution. So let's solve this again. So the solution is like here, the random variable x is what? The duration of baseball league match. Duration of all baseball league games. Duration of baseball league match. Okay, so duration may be anything, and here it is given it follows uniform with 427 hours to 504 hours. Okay, we need to find this. So let us first write the PDF. The PDF for this is like 1 upon b minus a. So it's 1 upon 504 minus 427. So it comes out to be 1 upon 77 when x ranges from 427 to 504. Hello. Is there anyone who want to ask anything? Okay, then it's 1 upon 27. This is the probability density function for the case. Now we need to find the probability that the team will play between 479 to 498 hours. So that means we need to find the probability that 479 to 498 hours. We need to calculate this probability only. Okay. Again, simple. Let's write it 479 to 498 fx dx. Simple. So it's like 479 to 498, 1 upon 77 dx. Now it's 1 upon 77, it's x, 498, 478. Just a simple integration and solution. Nothing here. It's 498 minus 479. Okay, am I writing it correct? Yes. So it's 1 upon 77 multiplied by 90. So the probability that 479 to 498 comes out to be 19 upon 77, which is approximately equal to 24% actually, 24.7%. Okay. So this means what? This means like a team will play the match between this has a 25%, approximately 25% chances that the match will be taken in 479 to 498 hours. Okay. Any problem or anything up to this point? Okay. So let's solve the next question here. Now the question is, assume that the time taken to finish a standard sized piece of cake, assume that the question is, assume that the time taken to finish a standard sized piece of cake by a 9-year-old child, by a 9-year-old child is uniformly, it's again from uniform distribution actually, it's uniformly distributed uniformly distributed between 0.5 to 3 minutes. It is given in minutes. Now, given that a child has been eating the cake, now the question is, given that a child has been eating the cake for more than 1.5 minutes, or more than 1.5 minutes, determine the probability that determine the probability that he or she will finish it. He or she will finish it in more than 2 minutes. Again, the simple question, assume that we are given some information like the time taken to finish a standard sized piece of cake by a 9-year-old child is uniformly distributed between zero point 0.5 to 3 minutes. Now we are given a conditional kind of a statement, that is, given that a child has been eating the cake for more than 1.5 minutes. That means the child has already eating the cake for more than 1.5 minutes. Now we need to find the probability that he will finish in more than 2 minutes. Okay. So the question is already written here. Now the solution is like, first, let me define the random variable. So the random variable is like time taken to finish or eat the cake. Time taken to finish the cake. And this follows uniform with parameter 0.5 to 3 minutes. Okay. So now the density function for this condition is like 1.3 minus 0.5 comes out 1.2.5. X lies between 0.5 to 3. Okay, so this is the density function under this condition. Now we need to find the probability that he or she will finish it in more than 2 minutes, given that he or she has been eating the cake for 1.5 minutes or more. So we need to find the probability that x is greater than or equal to 2. Sorry, it's more than 2, not equal to. So it's greater than 2, given that uh, x is already greater than 1.5. Okay. Actually, you may write equal to as well because it is a continuous distribution, and in continuous distribution, the probability at a point is 0. So you may write both. Okay, but according to the question, it's given the probability that x is greater than 2, given that x is greater than 1.5. Okay, we need to solve this. As we know the formula, people may recall, since probability that AG will be is what? Probability that A intersection B divided by probability of. This is already maybe people have remembered. So this means what? So it means probability that x is greater than 2 intersection or and both have the similar meaning. Let me write it intersection here only. X is greater than 2 intersection s is greater than 1.5 and probability that x is greater than 1.5. Similar question. Okay. Now you may see here, suppose it's 0, it's 1, it's 2, it's 1.5. Okay. If you say, if you see x is greater than 1.5, then this is the line. X is greater than 2, then this is the line. So that means what? That means these are the common points. So x is greater than 2. The common portion is x is greater than 2. So you may write here, like the numerator term can be written as probability that x greater than 2. You may write like equal to as well if you want. Okay. Or not. Probability that x greater than 1.5. Now, I think it's simple. Probability to fx dx, probability 1.5 fx dx. See, greater than 2 implies x is greater than 2 to infinity. But if you see the data we are given, the range is from only 0.5 to 3. Okay, so we stick to up to 0.3 only. Okay, so this means what? So it means 2 to 3, it's 1.5 to 3. Now the PDF is it's 1 by 2.5 actually. Okay, so that is 0.4 if you write. Okay, so let me write here. It's 0.4. So this means what? So this means it's integral over 2 to 3, 0.4 dx divided by 1.4 to 3, it's 0.4 dx. Obviously, it's very simple. Now 0.4 taken as numerator, x, it's 2, 3. Again 0.4, it's x, it's 1.53. 0.4 will be cancelled out. It's 3 minus 2 divided by 3 minus 1.5 comes out to be 1 divided by 1.5, which is approximately equal to 0.66667 or something 0.67. So the probability, what is the probability? The probability that x is greater than 2 given x is greater than 1.5 is comes out to be 0.67 or 667 or whatever you like to write. Or 2 by 3 even, you can write 2 by 3, quite famous. Okay, so up to this point, anyone have any doubt he or she may ask? Okay, anyone? Okay, now the next question. Let me write the next question then. Now the next question will be like, okay, it is based on the beta distribution. Now it's Maximum time to complete a project is 2.5 days. We are given maximum time complete a project is 2.5 days. Suppose the completion time, suppose the completion time as a proportion of this, as a proportion of this, of this maximum time is a beta random variable. With alpha equal to 2 and beta equal to 3. Now the question is, what is the probability that what is the probability that the project requires more than 2 days to complete? That the project requires more than 2 days to complete. Okay, so this is the question. Here, one thing you should notice, or you here see, the maximum time to complete a project is 2.5 days. Okay, now suppose the completion time as a proportion, the completion time as a proportion, because we are discussing about the beta distribution, and we know that it is a restricted distribution. That means its support is either 0 to 1, lie within 0 to 1. Okay, so obviously, so we need to use some proportion from scaling method. Okay, so the proportion is like obviously it's lie between 0 to 1. So the completion time as a proportion follows the beta distribution with the given parameter alpha equal to 2 and beta equal to 3. Now we need to find the probability that the project requires more than 2 days to complete. But as we have already known, the maximum time is 2.5 days. So let's solve the numericals. Now the question, I mean, the solution is like we are given. The first one is like X. What is X? The completion time. Okay. But in proportion. Because if it is not in proportion, then it invalidates the support for the beta distribution, which is 0 to 1. So in completion, sorry, completion time in proportion. So this means what? X follows beta distribution with parameter alpha equal to 2 and beta equal to 3. It is given actually in the question. And if you recall, you may find that the PDF for the beta distribution is like 1 upon beta function alpha beta. And it's x to the power alpha minus 1 and 1 minus x to the power beta minus 1. Here alpha beta greater than 0, x lie within 0 to. Okay, so this is the density function for the beta distribution. Also, where beta alpha beta comes out to be like gamma alpha gamma beta upon gamma alpha plus beta, and gamma n plus 1 comes out to be n factorial. So this is the case that we have already discussed in the above slide actually, but I've already writing here as well. Now the question is, we are given the value of alpha and beta. So let's write the PDF for those that alpha beta. So it's 1 upon, let me write first BA. It's beta alpha beta comes out to be, it's gamma 2, it's gamma 3 upon its gamma 2 plus 3. Gamma 2 comes out to be 1, gamma 3 comes out to be 2, gamma 5 comes out to be 4 factorial, that is 4 into 3 into 2. So overall, it comes out to be beta 2 and 3 comes out to be 1 upon 12. Okay, so this is the case. Now the PDF. Fx is 1 upon this, comes out to be 12, x to the power alpha minus 1, and 1 minus x to the power beta minus 1. So our probability density function for this case comes out to be 12x 1 minus x whole square. When x lies between 0 to 1, alpha is beta is greater than 0. So this is the case. This is the final probability density function form for alpha equal to 2 and beta equal to 3 when x follows the beta distribution of first kind. Now our question is to find the probability that it project requires more than 2 days. Okay, so we need to convert this more than 2 days into proportional form. Obviously, it's like it's 2 or the maximum days is 2.5. So obviously, it's 2.8. Okay, so we need to find the probability that x is x greater than or equal to 0.8. Okay, it will not equal to, it's more than only. Again, you may remove this sign. Probability that x is greater than 0.8. Now it's 0.8 to 1. It's fx. Fx is here 12 x 1 minus x whole square dx. Okay. Now if you open this, you may find 0.8 to 1. It's 12x. It's 1 plus x minus 2x dx. You may just simplify this so that it becomes easier to solve. And then you may find it's 12x plus 12x square minus 24x. Okay, here x is square actually. It comes out to be x cube and 24x square is this. 12x minus 24x square plus 12x cube dx. So this is the case. Now it's a simple integration. So let me write the integration 12x. So it comes out to be 12 x square by 2 plus 12 x to the power 4 upon 4 minus 24 x to the power 3 upon 3. It's 0.8 to 1. Now it's 6x square plus 3x to the power 4 minus 8x cube, 0.8 to 1. So yes, putting the limits, it's 6, 1. If you put the value 1 as x as 1, then it's 6 plus 3 minus 8 minus, it's 6 into 0.8 square plus 3 into 0.8 to the power 4 minus 8 into 0.8. Okay, so it 9 minus 8 comes out to be 1 minus 6 into 0.8 square and 3 into 0.8 power 4, and this I've already solved this. The value comes out to be, after overall solution, it comes out to be 0.9728. Okay, you people may solve this by a calculator or online. Okay, you may find it comes out to be 0.9728. And then the probability that x is greater than 2 comes out to be 0.0272, which is approximately equal to 0.03 because the given answer is 0.03. Okay, so this is the final solution. Anyone? Anyone have any doubt? Not, then let's go to the next question. Now the next question is like it is based on the exponential distribution. Okay, a good one. The question is like with an average of 10,000 miles, with an average of 10,000 miles, the number of miles a particular car may travel, the number of miles a particular car may travel before experiencing battery failure. Before experiencing battery failure is exponentially distributed. Is exponentially distributed. Now, the car owners needs to travel 4,000 miles. Now the question is, car owners needs to travel 4,000 miles. Now the question is, what is the probability that that the journey can be finished without that the journey can be finished without a car battery replacement. Okay, so it is already given in the question that the average lifetime for the battery is like 10,000 miles. Also, it follows the exponential distribution. Okay, so yes, we are already given some information. Let us first write those information. Now, x follows exponential distribution with lambda equals 1 by 10,000, so that we can write the lambda 1 by lambda equals 10,000. Now the PDF that we have discussed, it's lambda e to the power minus lambda x, or you may write 1 by lambda e to the power lambda by x. Okay. The value of lambda is greater than 0, x is greater than 0. This is given. Okay. Also, we have given one more information that like the average of 10,000 miles. So we are given the average. And for exponential distribution, the average is like it's 1 by lambda. It is given, actually, it is given 10,000. Okay. So from here only, the lambda comes out to be 1 upon 10,000. Okay. So we are given the parameter value, that is 1 upon 10,000 or 10 power minus 4. Now we need to find the probability that x, here if you read, We find the car owner needs to travel 4,000 miles. Okay. Then what is the probability that the journey can be finished without a car battery replacement? So the journey is about 4,000 miles. So without replacement a car battery, that means the probability, we need to find the probability that x is greater than 4,000 so that the journey is complete without car. Okay. So yes, this is the question. So it's 4,000 to infinity lambda e to the power minus lambda x dx. Okay, we are given the value of lambda and all. Okay. Also, you know that it's 1 minus 4,000. Okay, it's greater than. So if you, sorry, excuse me. Yes, here it is given x is greater than. So this is actually the survival or reliability actually. And if x is an exponentially distributed random variable, its reliability is e to the power minus x. Okay, it's totally e to the power minus x only. But here we can solve. We can solve like this. It's 1 minus, it's 0 to 4,000. It's lambda e to the power minus lambda x dx. Again, so this is the CDF actually. This is the CDF. So just if you solve this, you may find it's e to the power minus lambda x and from 0 to 4,000. Okay, and just solve this. You may find e to the power minus 1 upon 10,000 multiplied by 4,000. So the probability that x will greater than 4,000 comes out to be e to the power minus 0.4. So this is the final answer. Okay. You may write a note actually if you want, like here. If x follows exponential lambda, then probability that x is greater than x is nothing but e to the power minus lambda. Okay. This is the case. Now the next question is like, you may solve e to the power minus 4 with some calculator and all. Okay. Now the next question is based on a Weibull distribution actually. Okay. The question is given the life of an MRI machine. The life of an MRI machine is modeled by a Weibull distribution with cumulative distribution function and write CDF as well. Okay, let me write given by fx equal to 1 minus e to the power minus of x upon delta the power beta where x greater than or equal to 0. This is given where parameter beta equal to 3 and delta equal to 700. These are given. Okay. These are given in hours actually. Then the question is, what is the probability that the question is, what is the probability that the MRI fails before 350 hours? That the MRI fails before 350 hours. Okay, we are given the MRI machine's lifetime is modeled by Fable distribution with the given CDF. The CDF is already given with the parameter beta equal to 3 and delta equal to 700. Now the question is, find the probability that the MRI fails before 350 hours. Okay, so let's solve this numerical. So first, at the lifetime is given here, lifetime of an MRI machine before failure. Okay, so X follows Weibull distribution with beta equal to 3 and delta equal to 700 hours. Okay, so the CDF is already given, which is already written here. Okay, the CDF for this value can be written actually. If you want, we can write here. It's 1 minus e to the power 1 minus e to the power minus of x upon delta. So delta will be given as 700, the power beta, that is 3. So this is our given CDF. Now probability that MRI fail before this. So before this is implies probability that x is less than or equal to 350. So obviously this is the definition for the CDF actually. If you remember, you may find, since the CDF of random variable x is defined as x less than or equal to x. So this is the case. So yes, we can write directly with the help of the CDF above, put the value of x equal to 350. So yes, it comes out to be 1 minus e to the power minus 350 upon 700 to the power 3. Yes, simply it is nothing but 1 minus e to the power minus 1 by 2 to the power 3 comes out to be 1 by 8. And after solving 1 minus e to the power minus 1 by 8, just you may either leave here if you want, and if you want some more simpler form, then the formula is like 0.8825 actually. This value comes out to be this. So x is less than or equal to 350 comes out to be 0.1175. So this is our required answer. Okay. So any question or any doubt up to this point? Okay. So let's solve the next question then. The next question is like have some different properties actually. So obviously kind of the tough one from the previous. The given is, it is given as like the time needed to solve a problem has an exponential distribution. The time needed to solve a problem has an exponential distribution with parameter lambda equals 1 by 3. Now, the two students starts tackling the problem simultaneously. Tackling the problem simultaneously. We are given assume the students are working independently or their own. Assume the students are working independently on their own. At the end of the 2 minutes, now the question is at the end of the 2 minutes, what is the probability that at least one student has figured out, at least one student has figured out the problem. Okay, so this is the question. The question is like the time needed to solve a problem has an exponential distribution with parameter 1 by 3. Now the two students start tackling the problem simultaneously, assuming the students are working independently or their own. So we need to find the probability that at least one of the students can figure out the problem at the end of the 2 minutes. So let's start to solve the problem. Anyone have any doubt that how to proceed this problem? So here, since we are given two students, okay. So yes, let x1 and x2 be the two students, okay, and they solve the problem. X1, the first student, solve the problem or figure out the problem, and the second students solve the problem or figure out the problem. Okay, so here we are given x1 follows exponential 1 by 3, x2 follows exponential 1 by 3. These are the information that is given in our question. Okay, so we like frame the question in this manner. Now we need to find the probability at least one finishes by 2 minutes. Okay, so we need to figure out the problem that at least one student finishes by 2 minutes. This is our problem actually. Okay, at least one or both. So that means minimum of x1, x2 is less than or equal to 2. Okay, at least one, at least minimum of one is less than or equal to 2. So this is the question. Now just try to remember, since the probability that minimum of x1, x2 is less than 2, is it equal to 1 minus probability that x1 is greater than it's 2 and x2 is greater than 2? Is it okay up to this point? That means the minimum value is less than 2. Okay. So that means 1 minus x1 is greater than 2 and the comma is and intersection is there and x2 is greater than 2. Okay. We may write this as this also. Since we are given x1 and x2 are independent, it is given as an assumption. Okay. So since x1 and x2 are independent in nature, so this implies what? This implies 1 minus the probability of x1 is greater than 2 and x2 is greater than 2 comes out to be probability that x1 is greater than 2 into probability that x2 is greater than 2. Because if you remember, you may find out when x1 and x2 are independent in nature, then the joint probability is equal to the product of their marginal probability. Okay, so this is the necessary as well as the sufficient condition. Okay, so we can write like this. Now, since we know x1 follows exponential 1 by 3, x2 follows exponential 1 by 3, we may solve directly. Okay, so now what? Probability that x1 is greater than 2 is, as we have already here, if you remember, recall, uh, yes, this note. This note. Okay, greater than e to the power minus lambda x. So using the same concept directly, so we found out it comes out to be e to the power minus lambda 2 and lambda equal to 1 by 3. Okay, let me write direct lambda 2. It's good. It's 2 by 3. And probability that x1, sorry, it's x2 actually. X2 is greater than 2 comes out to be the power minus 2 by 3 again. Now the 1 minus e to the power minus 2 by 3 into e to the power minus 2 by 3 comes out to be 1 minus e to the power minus 4 by 3. Up to this point, is it okay? So 1 minus e to the power minus 4 by 3 comes out to be 0.264 and at last it comes out to be 0.736. So this is the probability that what is our required actually, that's long. So let me write the probability directly here. So the required probability comes out to be 73.6%. Okay. Also, there is one more note actually, like the minimum of x1 and x2 again follows the exponential distribution, you may recall. Okay. So yes, this is the question. We have some more question. Up to this point, is there any problem to anyone? Okay, the next question is like, suppose x is a random variable. Suppose x is a random variable with the distribution function with distribution function to be a beta distribution. Okay, beta distribution. So it's like beta, alpha, beta. Okay. The mean and standard deviation of X. We are given the mean and standard deviation of X, which is beta distribution, are 0.9, sorry, 0.09, it's not 9, 0.09 and 0.03 respectively. Okay. Find the parameter. We need to find the parameter. Find the parameter alpha and beta. Okay. Simple question. We are given X is a random variable which follow beta distribution. Here it is already given X follows beta distribution with parameter alpha beta. Okay. And expected value of X comes out to be 0.09 and standard deviation. Let me write it by ST. It's 0.03. So its variance comes out to be square of standard deviation, that is 0.0009. Okay, the variance is given 0.0009. Now the question is find the parameters. So how can we find? Just since we are given two conditions, the expectation and the variance are given. We have two unknown parameter alpha and beta. So obvious kind is like we will formulate two equation. Okay. So yes, X follows beta, then the mean value comes out to be alpha plus beta. Okay, alpha upon alpha plus beta. It comes out to be 0.09. Okay, let's assume let alpha plus beta can be equal to S. Okay, so because it appears a lot of time. So for alpha plus beta, we will treat S. So it comes out to be S equal to 0.09 times of N. This is the first condition actually. We are given alpha equal to 0.09 times the sum. Now we are also given one thing actually. If you find out from here only, beta is what? Beta is equal to S minus alpha, S minus 0.09. So comes out to be beta equal to 0.1 times of the summation S. Okay, so this is the second equation. Okay, now we use these two terms and find the value of the alpha and beta. This is the simplest, I think I can figure out. This is the simplest way to find the values. Now we are given variance. Variance of X is what? Variance of X is it's alpha beta upon it's alpha plus beta plus 1. It's alpha plus beta whole square. This is the variance for the beta variate, which is given 0.0009 given in the question. So yes, if you find, you may find it's alpha beta. It's alpha beta. It's alpha plus beta plus 1 comes out to be S plus 1. And this is S square, which is equal to 0.0009. Okay. Now, from here only, this is equation 3. Okay. Now, since from equation 1 and 2, alpha into beta. Okay. From equation 1 and 2, alpha into beta comes out to be 0.09 S multiplied by 0.91 S. simplification will be like alpha into beta comes out to be it's 0.0819 square. Okay. I'm just labeling the equation as 1, 2, 3, 4 so that I can directly use the term from equation 1, from equation 2, so on. So now from equation 4, using in 3, we will find out what alpha beta, which is 0.0819 s square. It's s plus 1, it's s square, it's 0.0009. Simple, s square can be eliminated. Now it's a simple equation with one variable, that is s. So yes, you may solve this. You may find s plus 1 comes out to be 0.0. Actually, after solving, it's 0.0819 divided by 0.0009. Just after solving, you may find s plus 1 equal to 91, not 19, 91. So it implies s equal to 90. Okay. So yes, s equal to 90. So alpha equal to 0.09 times of s comes out to be 0.09 times of 90 comes out to be 8.1, and beta equal to 0.91 times s equal to 0.91 times 90 comes out to be 81.9. So the value of alpha beta comes out to be 8.1 and 81.9 respectively. Up to this point, any doubt, any problem, how I have proceeded this question, anything, anyone? No? Okay then. So let's assume you have understand the question. Okay. So let's solve some more question based on one is based on like memoryless property actually. Now the question is, if x has exponential distribution, if x has exponential distribution with mean 1 by lambda, then find probability that x is greater than 3 given x is greater than 1. A similar kind of question is also like we have solved today, but for uniform distribution actually. But this is for exponential distribution. And if it is uniform, then we can't use the memoryless property. But if it is exponential, we can use the memoryless property. So now the solution will be like, since x follows exponential lambda, because the mean value is on the lambda. So exponential lambda is this. So fx will be like what? Lambda e to the power minus lambda x is greater than 0, x is greater than 0. Okay. Always try to write, whenever you are going to write the PDF or PMF, always write the support, the range of the parameter as well as the random variable. Okay. It gives the complete PDF format. What if I write x is greater than 8? Then it's not a PDF now. Then it's just a function, which is not a valid PDF. So it is called a valid PDF if the range or the support is already is also written with the functional form. Okay. Now the first thing is the probability that x is greater than 3 given x is greater than 1. This can be written as like what? Just I'm solving with the usual method. A given B. So its probability that x is greater than 3 intersection x is greater than 1 given by probability that x is greater than 1. So obviously x is greater than 3 and x is greater than 1. They both have a common portion of x is greater than 3. X is greater than 3. Probability that x is greater than 1. It is what? It is a exponential distribution. Again, so it comes out to e to the power minus 3 lambda, as we have already discussed as a note event, and e to the power minus lambda. So it comes out to be e to the power x is greater than 3 given x is greater than 1 comes out to be e to the power minus 2 lambda. Okay, this is the usual method. This is the usual method. Now let's use alternate method. So alternate method is what? As we know the memory property, probability of m plus n is probability of x is greater than m plus n given x is greater than m is equal to probability x is greater than. Okay. So again, the probability of x is greater than 3 given x is greater than 1 can be written as probability of x is greater than 2 plus 1 given x is greater than 1 comes out to be probability that x is greater than 2. Now again, it's e to the power minus 2 lambda, simple, which is equal to the previous one. Okay, so either you use memoryless property when you are dealing with the exponential random variable or a geometric random variable in case of discrete case. Okay, then you can use directly this property, otherwise go as usual. Okay, there is one more question actually, the last one. The question is like the percentage of impurities per batch in a certain chemical product chemical product is a random variable x that follows the beta distribution given by the PDF is given actually. The PDF is like this. You know the standard format actually. Here we are given the simplest form. Okay. When x lies between 0 to 1 and 0 otherwise. Okay. This is given. Now the question is, what is the probability that a randomly selected batch randomly selected batch will have more than 25% impurities. Okay. So given the impurities, the proportion of impurities or percentage of impurities follows beta distribution with the given PDF. It's a simple question actually. We need to find the impurities which is more than 25%. Just a simple calculation actually here. So we need to find the probability that x is greater than or equal to 25% implies 0 point. Okay, this is again a question. It's 25%. So this implies it's 1 by 4 in proportion, if you may recall. Okay, so 0.25 or 1 by 4. Okay, so comes out to be like integration 1 by 4 to 1 because the beta distribution has a maximum range support of 1 and the PDF is given as 6x 1 by x dx. Simple. You can write it's 1 by 4 to 1 6x minus 6x square dx. Simple. Okay. It comes out to be like what? It's 3x square minus 2x cube. It's 1 by 4 to 1. Simple. Now putting the limit, it's 3 minus 2 minus of 3 1 by 16 minus 2 1 by 64 comes out to be 1 minus 3 by 16 plus 1 by 32 comes out to be it's 32 minus 6 plus 1, it's 27 upon 32. So the probability x is greater than 0.25 is 27 upon 32, which is actually more approximately, I think, 82, 83%. It's more than actually 90%. I don't have the final answer. This is the final answer. It's 27 upon 32. Okay, so this is the case. So up to this point, is there anyone who have any doubt? Anyone? Okay, then if no one have any doubt, I think we should conclude our session here. Okay, so if anyone have anything to say or ask, you may ask, or we may end the meeting here. Thank you. Anyone? Okay, then let me first stop the recording.